Hello, and welcome to today's video where we'll be talking about the cubic equation of state. So in another video, I've already worked it out a little bit, did some stuff with it. This time around, I want to graph it, specifically in Python. And just to give a little preview, right, I'll specifically be doing the SRK equation of state. However, I will be putting in some extra stuff for van der Waals equation of state, but it won't be that big. Um, but just as a little preview, uh, this one right here, the one that I'm circling, uh, that's kind of what we're aiming for. And I'll switch back over to this tab a couple of times just to, sort of have a comparison so that we know where we're going. So let's get started. All right. So moving on here, let's look at the equation slash function that we're going to be working with to see kind of what road work we'll have to go through to get this thing plotted. All right, so we'll be using the generic cubic equation of state here. And to sort of differentiate between the different kinds that were made, van der Waals, RK, SRK, we have different values that are getting plugged in for these constants. So like I said, we'll be mainly focusing on SRK. And for the van der Waals, well, I'll add some stuff, but like I said earlier, it won't matter. So just to look at this equation a little bit more, we have our two values that we'll be inputting ourselves, right? And we have an assortment of constants that we have to work out. R, which is a singular constant, B, epsilon, sigma, and A, which depends on T. And as we look over here on this right side, we can kind of see how those values are calculated. And there's quite a lot here, right? So to make this a little bit easier on the coding and such, how about we sort of divide up the work in a way? You'll see what I'm talking about here in a bit. Let's work on these constants that need work, and from there, after that, we'll do the function part. So, and then after that, we'll do the plotting. So firstly, let's work on these constants. All right, so here we are in the Python portion. And so behind the scenes here, I've taken the liberty to sort of put everything that we need in the background in already. But I will take some time here to explain what I have actually put in. And so first line here, I'm copying some Git code that brings in the properties of all the compounds that we'll work with in chemistry. Specifically for this one, we'll be using water. And so I need the properties of water, and this brings that in. This import sys and path insert allows Python to actually see the code that I brought in. And I'm now specifically bringing in those tools that let me see the properties of water. NumPy for numerical calculations, right? Usual. This one will be in a later video, but I'll be working on the same notebook here, so I've already imported it. Plotly subplots, because we'll be graphing it, and this plotly templates is just a preference thing that I've added, right? It makes the graph background dark. And so let me run it. And while it's doing that, we'll sort of move on here to the actual coding portion, right? All right, so what do we need now? What is our first step? Well, like I said earlier, we need the properties of water, right? So let's bring those in. So I'll be labeling it as W, CHE dot props, and we'll call in the object water here. And another thing that we'll be using throughout the thing uh, is the constant r, right? So we might as well just code that in here now as well. All right. Now that that's done, let's look at our equation here for a second. So, like I said at the beginning of the video, let's kind of tackle the constants first, right? The constants that we'll be using in here, so that we don't have one large function code. So, what is a constant that we can sort of work out first? Let's do epsilon and sigma first, all right? And how do we know what epsilon and sigma are? Well, we use this table here, so it's pretty straightforward, and we'll start doing that. So let me define a function here. We'll call it the cubic because it's cubic equation, right? And we'll do it for these constants, a, b, e, and s. I'll leave that empty for now. All right, so since I did say we will do it for srk, I could just code in the sigma and epsilon, hard code those in as their own values, right? But let's say we want to use this specific code in the future, and we want to have the ability to swap between the different types of equation of states, right? For example, let's say I wanted to use van der Waals one day and then another day use SRK. So to do something like that, we would use this um, method, I guess you'd call it, called dictionaries inside Python, right? So for example, I could say when van der Waals, I'll type in all caps, is typed in, that value for epsilon, I believe it was 0 earlier, and if they type in SRK for their equation of states, I'll double check here to see what it was, also 0, and I'll put it in here, EOS, equation of state, and we'll make it default SRK, just so that I don't have to. And to sort of pull out a certain value from the dictionary, we need a key, right? And that key will be supplied by whatever EOS I put in when I call the function. And we'll be doing this a lot for a bunch of the other values as we go through for A, B, and sigma, right? So to save myself some time, I will be pasting these because we'll have, oh, oops, I did not mean to do that. We'll be having a lot of these. So the next one obviously is sigma. And van der Waals, I believe, was 0 as well. SRK, however, is 1. So now we have our epsilon sigma. So let's do our next constant. Let's do b. B seems fairly simple, right? So now we need a psi value. And the psi value, my bad, I meant omega. So this omega value is different between van der Waals and SRK, right? So let's do the van der Waals first. So I'll just do omega equals 1/8. I'll put decimals on all of this, so they all become floats. And SRK was a pretty lengthy decimal from what I remember. 0.08664, 0.08664. Now we have our omega. And what else do we need for our B value here? That's it. So we can sort of calculate that now. So for B, it will equal omega times R times the critical temperature of our compound, which will be water, divided by our critical pressure of water. All right. So now we have our B done. And the only other constant left that we have to work on is A, correct? So here is A. And as you can see, it depends on temperature, right? I don't know how to zoom in, but so this is what we'll be putting into A. So we have psi. Like I said earlier, it's the same with omega. It's different for whatever equation you're using. So let's put that in first. So for van der Waals here, psi will be 27 over 64. So psi for van der Waals will be 27 over 64. And SRK is also a pretty long decimal, which is 0.42748. 42748. 42748. And as you can see here, we have this alpha that A also depends on. And alpha also depends on the reduced temperature and the eccentric factor, which is this smaller, the lowercase omega. And for van der Waals, it's quite simple. It's just 1. However, for SRK, it is this very long equation. So that is our other thing that will vary, which the dictionary helps sort out. So like I said earlier, van der Waals was 1. And as you saw from earlier, it depends on temperature, right? Whatever the temperature is. So that will be the other value that goes into the function. And we also needed, like I said earlier, the reduced temperature. So that is simply the temperature. That is simply the temperature divided by the critical temperature. And we also need the eccentric factor, which is omega, which is represented by lowercase w. All right, so let's start putting in this really long code. We have to be careful, right? So I'll go real slow here. So 1, I'll put parentheses first. 1 plus we have 0.480, 0.480 plus 1.574 times the eccentric factor minus, I'll put this in parentheses just because I saw a square. We want to make sure it gets squared before everything else. So 0.176 times the eccentric factor squared. Eccentric factor squared. All right. And now all of that is being multiplied by this quantity here times 1 minus the reduced temperature square rooted. And that should be it. And now all of that is squared. All right. So that's our alpha. And just for now, we could see if it's working. So alpha, B, epsilon, and sigma. And let's try using it. Cubic ABS, some random temperature, and I won't put anything for EOS. All right, and alpha does return 0, 1. Alpha does return something. Let's hope it's the correct value. We'll see it in the graph if it isn't. All right. So let's work on our final constant, A here. So A is psi times alpha times r squared times r squared times the critical temperature squared all over the critical pressure. All right, and this should be our constants done, right? Our constants for our cubic equation of state. So let's check it out. I'll do 350 again, and SRK is the default, so, and there we go. And let's say we wanted to see van der Waals equals van der Waals. And we have that 0, 0. All right, so now we know it works. And now we can sort of move on to our next function, right? What is the function that needs these constants, right? The generic cubic equation state. So let's start writing that function. So quick thing, interjection here before I move on to the next part. I have discovered an error, and it's right here. I forgot a parentheses, and there's one too many over here. So quick fix, if we run this again, that should be the correct value for A. So there we go. All right, so let's move on to the actual function. So I've already deleted our test here, and let's start doing it for pressure, right? And so let's look at our function real quick. We have all our constants, so what's left, right? Well, V and T. So those are the things that we'll need to uh, give to it, right? So specific volume, temperature, and once again, our equation of state, that specific one that we're using, and it will just default to SRK. All right, sorry for hitting the mic there. What do we need for this? Well, our constants, right, that we just created earlier. And that's going to be coming from our earlier function. And that needs temperature and EOS. And what will it return? Well, the equation, right? So it is R times T over specific volume minus B, the excluded volume, right? Minus A over V plus epsilon B times B, and also divided again by the same exact thing, except with sigma now. And there we go. All right, and let's check if it works. I will do 1 cubic meter. Let's do it at 300 and SRK. And there we go. We have our value. All right, so now we can actually move on to the graphing portion now that we have everything function-wise set up. All right, so let's get started with the plotting portion, right? So uh, there, so a bunch of issues are going to pop up, and I'll I'll bring you guys through them as we go through them. All right. So we need volumes and temperatures. So let's get the let's get this that out of the way first. All right. So for now, let's do a random temperature. Let's do 300, and we need to supply this function with a bunch of volumes, specific volumes, right? So that we can get an actual plot. Now, let's say you would think you would use lint space, right? So let's 0 to 100,000. And let's do 200 points. NP dot space. And our pressures will equal cubic P, and it will be those V T. And what EOS is EOS. So let's try plotting this and see what it looks like. So fig dot add scatter. X is equals V, Y is equal P, and let's do mode equals, let's do markers. And as you can see, this looks nothing like that, and we have an issue. We're dividing by 0. So let's run through these errors one by one here. Firstly, humongous values, right? Humongous values. So let's for oftentimes in chemistry here, and we decide to plot these type of things, we do run into these humongous values, and the one solution to them is to uh, turn it into a logarithmic scale, right? So that's what we'll do here. Type equals log. That looks a lot better, right? Next error is this divide by 0. So we can't obviously start with a specific volume, 0, right? Volume can't be 0. That's numerically impossible because we would be dividing by 0 here. And it's also, conceptually impossible as well. So what volume would we start off with, right? And well, the first thing that comes to mind is, well, the volume can be as small as the excluded volume, right? The volume of the atoms and stuff. True, but if you were to plug that number into the equation again, right here, I was about to point at my computer screen, but you wouldn't be able to see that, so. But that would make it a divide by 0, which would still make this error occur. So we have to do just a tiny, tiny, tiny step above that. So how would we do that? Well, let's do 1% times b, all right? And well, we need to scale it with b. And right, I need to bring b into here. So let's do that. B equals this here. And since I'm only showing the plots of SRK, I can hard code this in as 0.08664. Oh, I have times there. All And wow. Still looks like doo-doo, right? And there's a big reason for that. It's because we're using lin space. We're linearly spacing these things when that wouldn't make sense right now that we have our axes on a log scale. We have to put it on a log spacing, right? So that our points actually look even on our scale. So that's what we'll do. We will do log space. And if we put it in, it still doesn't look right. Well, that's because log space actually it takes whatever we have as a starting value here and does it tend to that value. So to counteract that, right, we have to log everything. So np dot log, and this is so that we actually start at our correct values, right? Log 10. np dot log 10. And this is starting to look a little bit better, right? If I change it to lines here. It looks a lot closer to this, right? We see it. We're starting to see that little van der Waals loop. All right. Well, let's slowly clean this up, right? As we can see here, our values, starting over here, start to become the same, right? There is just this flat line. So we can sort of shorten that down by just having a value over here, just a value. We can probably go a little bit smaller. That seems fun. And now we have something to do with this y-axis here. Let's do something like this. And this works a little bit better. The temperature I have set, it's fine for this scale. And we can see this looks a lot better, right? Now, this is only one isotherm, and we need a bunch of isotherms, right? So we'll need a loop for that, right? To keep on iterating and plotting a new plot for each specific isotherm. So let's get started on that. All right, so let's start, making it look like this, right? We need all the other isotherms. So we won't be needing this, right? And we'll be needing a for loop. So it can iterate through all the different temperatures. So for range, let's start at 300 because anything below that will probably just get cut off by our boundaries that we've set. Let's go to 800. And let's step at 25 kelvins every time. And we'll need this. This will be iterated through every time. And this, so that it can plot it every time it runs through. I'll add some space here. And let's try it. And there we are. Well, doesn't look quite as good because of this long linear section, right? Straight line. Looks kind of ugly, so we can sort of change this again to maybe -3. Oh, whoops. There we go. That looks a lot better, right? And well, we have one final issue. We don't know what temperature is which, right? So let's add some names to them, right? And we will do an F string for that. It'll be the temperature at whatever value of temperature, right? Kelvin. and put that in, and voila. We now know, well, there's a bunch of isotherms, so it might still be hard to read, but this is how you would plot the SRK equation of state for water. And looks real pretty, and looks exactly like what it does on Wikipedia. Well, not exactly, because they don't have a few isotherms, but this is how it would look.